Okay. And we're going to take a look at a couple of new situations. So let me see here. All right, so trig integrals continued. Okay, so before we do that, we have some trig identities that we're going to need to make sure that we remember. The first one is sine squared plus cosine squared is equal to 1. And then the other ones, remember, you get them by dividing both sides by either sine squared or cosine squared. So since we're going to use the one with secant and tangent, if I divide everything by cosine squared, what would I get? What would this first one be? Tangent squared plus 1 equals 2 secant squared. Okay, so this one we're going to use today quite a bit. Okay, and then we have the two reduction identities, right? For sine squared and cosine squared. Do you guys remember those? 1/2, 1 minus cosine of 2 theta. And then cosine squared was 1/2 times 1 plus cosine of 2 theta. Okay, so it's important to know how to derive the reduction formulas. It's a good skill to have, but we're going to try to use reduction formulas the least as possible because our brain is already full of a lot of things to memorize, and so adding more things to memorize is not exactly the most efficient use of your brain. So, but these are important to memorize, so. But I think you will all agree that memorizing those identities is a lot easier than memorizing the 6 reduction formulas. You guys agree? Yes. Okay. All right. So what we're going to take a look at today is products of trig functions. So first, let's take a look at products of sines and cosines. So what we want to take a look at is integrals of the form sine raised to the mx times cosine raised to the nx. Okay, so we've already done some of these. So we already saw that. So like, for example, here's an easy example. If I have sine, let's say, to the 12th power, and then a single cosine. That's pretty easy, right? Because it doesn't really matter that sine has such a big power. What would you do to find that integral? Yeah, you just use substitution, right? Here you would just let u equal to, so you would let u equal to sine x, right? So then dx equals to cosine x dx, right? Okay, now, but what if I change that from just cosine? So I have only cosine. Let's say I change that to cosine to a different power. Let's say I make it cosine to the 3rd. Any ideas on what I would do there? I'll give you a hint. It's not that bad.
You can break sine up.
Break what up?
Sine.
Close. Close, close, close. Not quite breaking off sine. Would I still be able to use the same substitution?
Yeah.
You can, right? Because so what you basically need to be able to use a substitution is you need to have the cosine of x by itself, right? So let's rewrite this one. So let's rewrite it as sine squared x. And then let me break off a cosine x. Okay, so what is it? Sorry. Okay, this would be cosine squared, right? You guys agree? Okay. All right. Let me put this in parentheses. Okay. Now, so can I use the same substitution still, where I would let u equal to sine, and then du is cosine x dx? How would I deal with this extra cosine squared? Yes, exactly. You would use a trig identity, this one right here, right? The first one, to change this cosine squared into, what would it equal to? 1 minus sine squared x, right? Okay, so then what we would have is, and we won't finish the whole thing, but you guys can see the idea. This is going to be sine to the 12th x times, instead of cosine squared, it's going to be 1 minus sine squared. And then times cosine x dx. And so what's going to happen is that you'll have, if you let u equal to sine of x, this is going to be u to the 12th, right? 1 minus u squared, and then cosine x dx, that's equal to du. So all we have is just u's raised to powers, and that we can find, right? What would be your next step to finish this off? Finish off the integral. Distribute, right? So you distribute the u to the 12th times 1, and then u to the 12th times u squared, right? So you'd have u to the 12th minus u to the 14th, and then you can find the antiderivative. Go back, right? Does that make sense, the idea? Okay, now, what made this possible? What was the key thing that made all of that stuff possible? Well, right, we were able to change this to 1 minus sine squared, but what else? Or I guess maybe another way to rephrase it is, how could I break it so that it would not be as easy to do as I just did? Change the cosine to the 4th. So see how, so we'll write this down in a minute, but let's say hypothetically this was cosine to the 4th. Do you guys see the problem with that? Why that would cause a big snafu for us? No? Okay. Well, let's do it. Let's take a look here. Okay, so I'm going to change this to a 4th, and we're going to watch how it breaks, how it gets destroyed. So what is this cosine going to be now? If this is to the 4th, this one is going to be cubed, right?
Didn't you just plug in that twice? 1 minus sine squared for each cosine squared? And then there's just a function.
Well, okay, we'll talk about that in a minute. But see, this wouldn't work out, right? Because cosine to the 3rd, do I have an identity for cosine to the 3rd? No, right? So this procedure and this substitution that I did would not work because I would have to have a cosine squared, and you can't. So then you might say, okay, well then scratch that. Let's say I get rid of this cosine and just leave it as cosine. Let's say cosine squared times cosine squared, right? And let's say you change both of these to 1 minus sine squared. Would that be a good idea? What would you have? If you change both of those to 1 minus sine squared, you would have a lot of stuff, yes. But what would they look like? We won't do it because...
all these signs.
Yeah, a bunch of sines raised to powers, right? Sines raised to powers. And so, theoretically, you could find it, right? And you would have a bunch of sines with powers, and you can use a reduction formula. How many times? A lot, right? Because it's to the 12. Madness. Okay. All right. So let's write some of these things down. So you guys agree that this is a bigger challenge. So I think you guys will agree that the easy case is if either m or n is odd. This is easy, right? So what we're saying here is that if the degree of either sine or cosine is odd, then that's easy, because then what can you do? You can always break off one of them, right? Just like we did in the first part of this example. You break one off and then you just use substitution. Yes? Break one off, substitution. Okay. So if either m or n is odd, no, not burr, break one off from the odd one and use substitution. Okay, so that's the easy case, right? Okay. So now, as long as either sine or cosine is odd, then we're good to go and we can do that. Now, let's say that we have, so suppose, so we'll write this down. This is the more difficult. So let's say instead of at least one odd, let's say that they are both m and n are even. Okay, so let's try to get the idea here. So before we write down a general strategy, so let's say we have sine squared times cosine to the fourth x, something like that. What do you guys think? Well, you can always go Wolfram, yes. But you're on a desert island. Wolfram doesn't exist.
I'm doing integrals.
You're on a desert island, and you've gone mad, and you've decided to just do integrals.
I'm doing it in the sand too.
I've got nothing else to do. I might as well just integrate. What would you do? What would you do?
A message in a bottle.
Message in a bottle. I don't even know what that means. Oh, there's like that. Oh, that reminds me of that song. This is actually way before your guys' time. Isn't there a song? Message? Yeah. Obviously. This is not, I'm not getting any street cred by bringing that up. Okay. So, yes,
Sine squared to turn to cosine.
okay, take the sine squared and turn it to cosine. Okay, that's a reasonable enough idea. Sure, why not? Okay, so Andrew says, well, what if we change the sine squared into cosine? So sine squared is equal to 1 minus cosine squared, and then times cosine to the fourth dx. Okay. And then what? Okay, fair enough. We'll distribute. So if we distribute, this is equal to cosine to the fourth x minus cosine to the sixth x dx, right? And then?
You have to go backwards now. And you divide cosine the fifth one. And you turn that back into a sine. So
What?
you-
No. Oh, turn everything now into sines?
No, just the.
Can you just integrate
How?
carefully?
Well, no, because see, the problem is, okay, so let's go back. This is important. Because remember, what made the other one so easy was because we had an extra trig function, right? That allowed us to do substitution. So here, we've got a significant problem on our hands. But we do have, so we have cosine to the fourth and cosine to the sixth, right? We do have these reduction formulas. Do you guys want to use those?
Yeah.
So you can either, okay, so we can either use these, or what's another option? Can you guys think of another option? Hint, we did it last time. Hint, hint. No. We spent like 30 minutes on Friday doing it.
Reduction formula?
Yeah, reduction formula, right?
Great.
Why else would we have derived them? Okay. All right. So, what did we do? Great. That's exactly what I wanted to hear. Okay.
We have to derive it first, though.
We have not derived the one for cosine. I think it's actually on your homework. So, okay. This is, all right, let's do, Okay, let's do this. Right here in this little box, I am going to, you guys are going to tell me what the reduction formula for cosine is. So cosine to the n x dx is equal to, so, okay, I'm going to do something first. I'm going to rewrite this as cosine to the fourth x dx minus the integral of cosine to the sixth x dx. Okay. What is it?
We have, she said the book says n over 2. Or like, instead of that n right there, it should be 2.
No, it's n.
It's right there.
No, you're looking at the wrong one.
Huh.
Or the book made a typo. I'm trying to open it. Oh, yeah, that's a mistake. I don't know why I thought it was Okay. All right, so we're going to use the reduction formula. Now, do you guys have any advice for us? So, okay, notice, this integral, we have to use the reduction formula how many times? Twice, right? Because every time you use the reduction formula, you reduce the degree by 2. Here you have to use it 3 times. Okay, so that's a total of 5 times. Okay, how about we simplify our lives? How? There's a quicker way. What can we do? Help me out here, guys. You guys see it? Instead of doing it 2 times here and 3 times here, you can do it once on the bigger one, and what's going to happen to it? Yeah, it's going to equal this one, right? And you can combine them. Okay, all right, so let's do that. That's the plan. Okay, so this is equal to, so I'm going to rewrite the first one. Cosine to the fourth x dx. Okay, and then this one we're going to use the reduction formula. So this is going to be minus, if I do the reduction formula with n equals to 6, this is going to be minus sine x cosine to the n minus 1, which is
Perfect.
5, right? And then over n, which is 6. And then minus n minus 1 over n. So that's going to be 5 over 6, the integral of cosine to the fourth x dx. And so see how these two you can combine, this one and this one. So this is going to be 1 integral of cosine to the fourth x, and then minus 5/6 cosine to the fourth x equals to,
Is it not plus 5?
Yeah, isn't it supposed to be?
aha.
Distribute the negative.
Gotcha.
Is it plus?
No, it's minus.
It is plus, but then you distribute the minus and then it's
Yeah, you have to be careful with your distributing. We have to distribute the negative, right?
what negative?
So this negative came from this negative that we had to distribute. So the reduction formula is positive, but we distribute the negative. So they both are negative.
So you can do that. You could add up integrals.
Yeah, of course. Because this is 1 integral cosine to the fourth minus 5/6 integral. Yeah, Tom? You guys are good? Okay. All right, and then we use the reduction formula again. 1, 2, 3, go. 1/6 times
Sine, cosine cubed.
sine cosine cubed over 4, okay, plus, how many? 3/4, right? N minus 1 over n. Integral of cosine squared x dx. And then minus sine x cosine to the fifth x over 6. Okay, and then this is equal to 1/6 sine x cosine cubed x over 4 plus 3/4 times, one last time, reduction formula there. I'll just write down the last part here so that we have it. Cosine to the 5th x over 6. Okay, so if I use the reduction formula now on cosine squared, this would be, what would it look like? Sine x cosine to the 1, right? X over 2, and then plus n minus 1 over n. So this time n is 2, right? So this would be 1/2. Okay, so this would be 1/2 the integral of cosine to the 0, which is 1, and the integral of 1 is x. So 1/2 x. Okay, and that's it. That's all you had to do.
Is there a simpler way to get
No, but, well, there is another way, and this is the way I would recommend you do it when the exponents aren't as large. Let me show you. Okay, and I won't do the whole thing, but I'll give you the idea. If you have, so like let's say hypothetically you have sine squared times cosine squared. So if the exponents are big, then the best thing to do is to use a reduction formula. If they aren't that big, you can do, so like for example here, notice that we can use some identities to simplify this a little bit. You can use the reduction identities, right? You guys want to use the reduction identities? So like this would be the integral of, what's sine squared? Sine squared is 1/2 minus cosine of 2x, right? And then what's cosine squared? Ooh, minus 1/2, sorry. 1/2 plus cosine of 2x dx. And if you multiply this out, you would get, ooh, I forgot the 1/2 again. What would that equal to? 1/4 minus 1/4 cosine squared of 2x. And then what can we do with the cosine squared of 2x? You can, what? Without doing reduction formula, you can do it again, right? The same exact formula identity that we just used to go from cosine squared to 1/2 minus 1/2 cosine of 2x. You can use it again. So doesn't this equal to the integral of 1/4 minus 1/4 times 1/2 minus 1/2. Yes. Okay, cosine of, what would this be? 4x, right? Because it's 2 times this one, so 4x. And so that you could do, right? Because you would distribute, and then each one of these, it's just one simple trig integral, right? Okay, so in summary, what do you do if they're both even? If they're both even. So,
A reduction.
yeah, so either use a reduction identity, And we'll put here if the exponents are small. The reason why you don't want to do this if they're big is because notice how, like let's say, for example, this was cosine to the 4th or to the 6th. You could still break it up, but you'll have a binomial raised to a power, and so that will expand, and it can get quite big if the exponent is big. So that's why you kind of want to avoid doing that if the exponents are big. So you can use a reduction identity or convert into the same trig function and use a reduction formula like we did the first one. Okay. So that's the plan. Okay, so questions? What do you guys think? Kind of involved in that, too bad. Yeah?
Just a little one. When you use the identity again in the bottom line, is that supposed to be 4x squared, or is it just
No. No, because so this
because it's 2 times whatever's in the
so this right here
yeah.
is that one. So cosine squared theta is 1/2 plus 1/2 cosine of 2 theta. So whatever is inside that gets multiplied by 2.
Okay, I was thinking squared.
Anything else? Okay. So this is a strategy. So it's easy if any one of them are odd, then it's easy, right? Break one off and use substitution. If they're both even, then turn one into the other and then use reduction formula or reduction identity or the reduction formula. Thumbs up? Yes, sir.
I have a question.
Yes.
Is that supposed to be 2dx's or is that
Yeah,
supposed to be
Okay. All right. Now let's take a look at tangents and secants. So let's say, what about it when we have products? Products of tangents and secants. Okay. So this is what we want to take a look at. Tangent to the mx times secant to the nx. Okay, so can you think of what would be the easiest case? Something that would allow us to use substitution? Kind of like the easy case with sine and cosine? Okay, yes, that is exactly right. If n is even, then this would be relatively simple, right? Because, all right, so let's write this out. So let's say you have tangent, I don't know, tangent to the 4th x and then secant to the 4th x, for example. So we won't do the whole thing, but we'll just talk about the idea. What would be your strategy if you're going to, if n is even, so here we have the power of secant is even, what would you do? You, yeah, break off a secant squared, right? So this one you would break it into secant squared, right? And then what would your substitution be? U equals tangent, because the derivative of that is secant, right? Okay, so that would be your strategy. So you would break off secant squared and use u equals to tangent x as your substitution. Okay, and then what would you do, like for example in this case, if you have any extras, what would you do with that extra secant squared? What can you do with it? Use it as a what?
Use the identity.
Oh yeah, use the identity, right? You can turn secant squared, you can go from secant squared to tangent squared. So it's really similar to the sine and cosine case, right? Secant squared is equal to 1 plus tangent squared, right? So you can easily just, your strategy is the same. It doesn't matter what power secant has. As long as it's even, you can always break off the secant squared, and then any extras you can just turn into tangents. Okay, now, what if, so that's good. So that's an easy case. Can you guys see another relatively easy case? M is odd. Okay, let's take a look at that. Let's see if we can come up with something for that one. So if I have the integral of tangent, so let's make it odd. And then secant. Okay, so first I'll write this down and then we'll talk about it. So if this one, notice that, so tangent's odd, right? Has an odd power. And then secant has an even power. So here I could just use what I just talked about up here, right? Since secant has an even power. Now let me change that now, and let me make that into an odd power. So now we can't use the same method that we talked about using in the first case, right? Because if I break off the secant squared, then you would have a secant by itself, and you can't turn the secant into a tangent easily and do all the same stuff, right? It's only if you had a secant squared. Okay, so but because I have my tangent is odd, what can I do? What would you break off? Mm-mm. So notice that up here on this first case, we let u equal to tangent. What if we let u equal to secant x? What would we need to have inside of the integral so that would work out? Secant tangent, right? Because the derivative of secant is secant tangent. So notice that if tangent is odd, you can break off a secant tangent, right? You can break off a secant x tan x and use this. So let's try it on that one, see if it works out. So this is equal to the integral. If I break off a secant x tan x, and then I write this as tangent cubed. Oh, sorry, not tangent cubed. What would that one be? Tangent squared, right? And then secant. So you break off secant tangent, and if I let u equal to secant x, du is secant x tan x, would that work out? As long as this would always work out, right? Because this right here is secant x tan x dx, that's du. U is secant x, right? This is u. And then what would I do with the extra tangent squared? Yeah, this is going to be tangent squared is equal to what? Secant squared x minus 1. And then again, you would have a bunch of, u's raised to powers that you can easily find. So this works if m is odd, right? Tangent has an odd power. does it still work even if I change this to, instead of to the fourth, if I change this to, let's say 6? Would that still work? Still works, right? Because then what would happen? What would this change to? Instead of secant squared, in this case, this would be secant to the 5th. And if you do the same substitution, everything works still just fine, right? On top of that, what else could you have done instead? Now that secant has an even power, you could have just done this one too, right? The first method. So either one would have worked in this case. Does that make sense? Okay. Now, what if, so what's the only case that we haven't done? So we did n is even, m is odd. What about if n is odd and m is even? So if I have tangent, I don't know. M is even. So this would be tangent, for example, tangent to the 4th times secant cubed. Then what can I do?
Split it up into like sine to the 4th x over cosine to the 4th x.
Interesting. Sine to the 4th. Yeah, that wouldn't work because of the powers. If there wasn't a bunch of them, I would say that might work, but you would have sine to the 4th over cosine to the 7th, and you can do substitution with cosine, but then you would have a bunch of extra signs on top that you can't really do anything with. Any other ideas? So neither of these work, right? Because if you break off a secant squared, you would have, and let u equal the tangent, you would have an extra secant that you don't know what to do with. If you break off a secant tangent, you would have an odd power of tangent that you need to turn into secant, but you can't because it's an odd power, so you wouldn't be able to do it. So what do? What's your last resort? Reduction formulas. So your last resort is to use a reduction formula. Now, how would I use a reduction formula? What would I need to do? How would I need to change that so that I can use a reduction formula?
Put them all into one side.
Yeah. So which one can you turn into the other one? Tangent into secant. Why is it tangent into secant? Yeah. So you would have to work on the one with the even power because that's the one that those are the identities that you have. So convert tangent to the mx into let's say in terms of secant. Secant and use a reduction formula. So like right here, tangent in this example, tangent to the 4th would equal to, what is tangent to the 4th equal to? So secant squared x minus 1 squared times secant cubed x dx. And so you can see why this is the most annoying case, because you have to, we won't do the whole thing, but you'll see in a moment. What is the first parentheses equal to? What is that equal to? Secant to the 4th x minus 2 secant squared x plus 1, right, times secant cubed x dx. And then distribute, right? And these powers, these aren't even that big, right? It's 3 and 4. Imagine if they were bigger. So this is going to equal to secant to the 7th x minus 2 secant 5th x plus secant to the 3rd x. And then here, well, you would use a reduction formula on secant to the 7th, right? And then that would mean you would get an integral with secant to the 5th. And then that one you could combine with this one, right? So you would have an integral with secant to the 5th, and then you would use the reduction formula with secant to the 5th, and you would get a secant to the 3rd, and you would combine that one with this one. And then you use the reduction formula again with secant to the 3rd, and it would turn into secant to the 1, right? And then you get the integral of secant. And you take a deep breath. And that's what you would do. Okay. Have a nice day. See you guys tomorrow.